Well, thanks. So again, appreciate the opportunity to speak before this forum today. We'll talk a little bit about NuScale, the technology, where we are in regulatory space and commercialization space. But first, just a word of what problem are we trying to solve? I think whenever you're looking at a new technology. So providing this background, if you will, I think is important to understand the global view of what nuclear energy can provide and SMRs in particular. So the reality as we stand today is that over 1 billion people globally live without any access to electricity. By 2025, it's estimated that half of the world's population will be living in a water-stressed area. Presently, over 1 billion metric tons of food is lost or wasted each year for lack of cooling. And all of this is within the backdrop of global warming, CO2 emissions, air pollutions, and that's been very well documented and discussed. So what is NuScale's mission? What are we trying to accomplish? What we're trying to do and what we are doing is providing a scalable, advanced nuclear technology for the production of electricity, heat, clean water to improve the quality of life for people on a global scale. So how are we doing that? So our 4 pillars are that it's smarter, cleaner, safer, and cost competitive. What we mean by smarter is that it has a flexible design. It can support a number of applications. It integrates very well with renewable resources, solar and wind, can provide highly reliable power to mission critical facilities like hospitals, things of that nature. And it can serve also as a clean baseload. By cleaner, what we're talking about is that it is 100% carbon free. It's as clean as wind and solar, but in a much smaller footprint. What do we mean by safer? Well, should it become necessary for the NuScale SMR to shut down, it can self-cool for an indefinite period of time with no operator action, no external water, and no AC or DC power. And from a cost competitive point of view, and this topic has been touched on in previous discussions, it's much less complex than a typical nuclear power plant. Offsite fabrication of the modules being done in parallel to the civil works in the field allow the plant to be built in roughly half the time because you're doing 2 things in parallel rather than in series. And again, what you're looking at then is an installation process, and we'll talk a little bit about that as the modules get brought to site. So a little bit about NuScale, just to step back a little bit from a point of background. NuScale was formed in 2007 for the purpose of completing the design and commercializing the small modular reactor, specifically the NuScale power module. The initial concept was developed and tested, has been developed and tested since 2000 as part of a Department of Energy program, the multi-application small light water reaction program. And this is where a lot of the fundamental principles were identified and tested and demonstrated, specifically when we talk about passive cooling and natural circulation. In 2011, a very important milestone was Fluor, a global engineering and construction company, became a lead investor in NuScale in 2011. And that did 2 things. One, obviously, it provided significant funding to allow us to continue to demonstrate our technology for the regulator and proof of principles and things of that nature. But also from a commercialization standpoint, Fluor has been instrumental in reviewing our design from a constructability point of view. So we're at a point now as we start construction projects, if you will, where we have a fairly high level of confidence that what we've designed can be built both in the factory and in the field. In 2013, another significant milestone, and that is that NuScale won a competitive DOE funding award from which over $300 million has been made available to NuScale to advance its design and again to demonstrate the technology. To date, NuScale has developed over 530 patents in nearly 20 countries. We have over 400 employees in 5 offices in the United States and 1 in the UK. And as Anna mentioned earlier, in August of 2020, NuScale's design was approved by the U.S. Nuclear Regulatory Commission, which is a significant milestone and a daunting task, if you will. And we'll talk a little bit about that. To date, the total investment in NuScale has been greater than $1 billion US. So a little bit about the technology and how it works. This is at the heart of the power plant is the NuScale power module. It's an integrated package which includes the reactor vessel, the steam generator, the pressurizer, and the containment vessel. Again, an integral package that is factory built. Each module is capable of producing 77 megawatts electric or 250 megawatts thermal, small enough again to be built in a factory, and each module has its dedicated power conversion system. So one module, 250 megawatts thermal, hooked up to one turbine generator producing 77 megawatts. And that has significant benefits when we speak of flexibility, scalability, being able to load follow. Again, we'll talk about that in a bit. Our flagship design is can house up to 12 modules or up to 924 megawatts gross electric output. But again, because of the scalability, smaller number of modules, smaller reactor building, 4 module designs and 6 module designs for 300 and 462 megawatts electric are also being developed, designed, and are available. So this is a picture of what you might see as a typical nuclear power plant. You have the reactor vessel, you have a pressurizer as a separate component, you have a steam generator again as a separate component, piping, reactor coolant pumps. And so what we've essentially done is remove all of these and replaced it with that integral package we talked about. Okay, so the containment vessel is on the outside. The pressurizer is integral to the module. Steam generators are integral to the module. Reactor pressure vessel, the reactor core. Just to clarify a point, this design it requires that the fissile material be installed, the reactor core be installed at site. It's not installed at the site. So to the extent that this is a vessel without any active nuclear components in it, is then shipped to site and then fueled at the site. But this module stands about 25 meters high and about 7 meters wide in diameter. So we talked about the fact that each module is aligned to its own turbine generator. Again, I'm not going to get into the details of this, but this is a schematic that shows that relationship between the module and the turbine generator. The turbine generators themselves are commercial grade, so that's an advantage from the standpoint of allowing a broader range of participants from the supply chain point of view. Again, we're looking at 250 megawatts thermal, 77 megawatts electric, much more available. Also, to the extent that I think Eric earlier spoke about the challenges associated with constructing a nuclear power plant in the field. The turbine generator building is not nuclear grade, it's commercial grade. And so that reduces the on-site risk and the things that have to be done on site when building the plant itself. So we talked about the module. This is a cutaway of a 12-bay building. You see 6 modules on the far side, essentially, and there'll be 6 modules on the near side. The entire building, all of the modules are submerged within the building by 6.5 million gallons of water in this particular case. The refueling comes in from the left. As you can see, there's actually a module in the crib that's coming into the space. Spent fuel pool is also within that construct. This is the building itself is below grade. It's aircraft resistant, and again, this design has been reviewed and approved and demonstrated to the regulator. So we have the module going into the building. The building down in the right-hand corner sits in the middle of the plant, if you will. What you see on either side of that 12-bay building are 2 turbine generator buildings. Each turbine generator building houses 6 turbine generators in this particular construct. Again, what this provides, again, from a safety standpoint, no operator controller action required in the event that it needs to be shut down, no external AC or DC power, and no additional water. The amount of water that's in the building itself in which the modules are submerged is sufficient to allow the reactors to be cooled down indefinitely. The other point that I think was raised earlier was location, and we could talk about this some more from the standpoint that the emergency planning zone, it's been demonstrated, extends only to the site boundary. Typical gigawatt size plant has an emergency planning zone of 10 miles. So to the extent that you may want to replace a coal-fired plant at the same location, taking advantage of its transmission lines, switch gear, and whatever assets may be reusable at that site, this construct will allow that to happen if the town, let's say, has built around the coal-fired plant and allows an emergency planning zone that's, again, at the site boundary. Just a word about the thoughts along coal replacement. We have done a fair amount of studies to evaluate the applicability of this design in replacing coal-fired plants, and we're pleased with the results that we've seen. We understand and appreciate that coal plants in many communities may be one of the larger employers, and so to the extent that we can reutilize many of those same employees to operate this plant is very likely. And the reason we say that is once you produce the steam and you go into the secondary part, the balance of plant, it looks very familiar to what you would find in a coal-fired plant. You're turning steam into electricity. The source of the steam in this particular case is nuclear, and a coal-fired plant is coal, but the steam itself and everything that's associated with the utilization and the conversion of steam to electric energy is similar. And again, many of those same employees or skill sets are applicable in this construct. So again, 12 modules is our flagship, but because of the scalability, you can reduce that to 4 or 6 modules. So just to sort of summarize a bit, looking at the numbers here from 1 through 5, factory fabrication, we have agreements with BWXT in Ontario, Cambridge, Ontario, and Doosan in South Korea to help us in the fabrication of these modules. I would add that Doosan is an investor in NuScale, and we're pleased to have them on board. The module itself, going to point number 2, is integral. It includes a containment and a reactor vessel. It can be shipped by truck, rail, or barge in as little as 3 pieces, depending on the location that it may ultimately go to. If it's on near a large body of water, as an example, gets installed into the plant, which I think is, again, it's a difference relative to what has traditionally been done with nuclear power plants, where you're doing that nuclear work, if you will, and construction in the field. Here, that nuclear work is being done in a factory where, in a much more controlled environment, with experienced fabricators in the nuclear industry having that culture, and then shipped to the site. And essentially what you're looking at is an installation process where those modules are put into the containment building. So what can you do with the output coming from a NuScale SMR? We've talked about the fact that you can operate an oil refinery. We've done studies where we can demonstrate and show that it can support hydrogen production. It can be used as a source of energy to provide desalination. It can integrate very well with wind. And again, regarding mission critical facilities, because of in this case, let's say 12 modules, 12 independent shafts, 12 turbine generators, the reliability factor is very significant, is very high. We've shown 4 nines to 5 nines as far as reliability. So when you're dealing with a data center, a hospital, things of that nature, the multiple shafts and what that provides you from a reliability standpoint is very significant. So a little bit about load following and integration with renewables. So there are 3 basic tools that allow this plant to load follow. And for reading from left to right, there's a turbine bypass. Again, because the turbine generator is relatively small, you can do 100% steam bypass of the turbine without tripping the turbine or tripping the plant. So that's a feature that, because of the size of the plant, is available to those that wish to integrate an SMR with available wind, solar, other intermittent sources of energy. If you could predict that the generation of other sources, let's say, was beyond an hour or up to a week, down powering the modules is another alternative, using the control rod drives as a mechanism to raise and lower the rods in such a way to modulate the power of each individual module. And then shutting down a module is also an option if you know that you may not need the power for a week, and being able to come back in a relatively short amount of time is an option. Again, taking advantage of the multiple shafts that this plant design provides. So speaking of commercialization, this is the mountain that we've been climbing, and it is a significant mountain. Starting at the bottom, we spoke about the DOE program that started in 2000. We are approaching the peak. We have received the NRC design approval. We'll be ordering forgings here within the next couple of years, next several months actually, working toward fabricating the power modules themselves. From a availability standpoint, we are on path to produce modules and make modules available for a plant as early as 2027. At this point, we're supporting a specific project, and we'll talk about that in a second. But this is just a pictorial representation of what we've already discussed to a large degree. So a little bit about the licensing process and the licensing application process as it relates to the US NRC. NuScale developed its design certification application. That was completed in December of 2016. It was submitted and docketed by the US NRC in March of 2017. And that design was ultimately approved in September of 2020. So 2.5 years of work went into evaluating the application. The application itself was over 12,000 pages. It included 14 topical reports, over 2 million man-hours of work, 800 people, 50 suppliers and partners, and a cost of over $500 million. And so when we talk about the challenges in licensing and we talk about investment, that last bullet is equally important from the standpoint of raising sufficient funds to be able to fund and finance this effort. It's not insignificant, and it can be very challenging, and sometimes could negatively affect the schedule of ultimately completing the licensing process. So a little bit about cost. That's always a topic of discussion. So for the purposes of this evaluation, we're again using just a standard 12 module plant. As I mentioned earlier, our lead investor is Fluor. They've been an active participant in development of the design, and they've been an active participant in helping us provide and develop Class 4 estimates as far as the construction of the plant. So this particular scenario, if you will, adheres to a AACE Class 4 estimate from the standpoint of the rigor that's involved in developing this estimate. Includes over 14,000 lines of equipment, material, information that's used to price this particular plant. Just to clarify, the basis of this plant uses generic Southeast US site. So what's included in there is the labor, productivity rates, supply chain that's available to that region. Fluor has the capabilities to modify this estimate to virtually any region in the world based on the variables that are associated with that region. And so that's the labor costs and productivity rates came from Fluor. As far as the module itself, that's based on a Class 3 estimate. It's a little bit more mature. We understand that we've developed that more completely. We have a manufacturing bill of material. We evaluated welding processes and machining and non-destructive testing processes as part of that. We've identified transportation costs again to the southeastern site, and again, $2,850 per kW is a fairly competitive number when looking at alternatives and looking at integrating this from a reliability standpoint. So just a word about our first contract. It's with the Utah Associated Municipal Power Systems. This is a project-oriented organization. It is scheduled to deploy at the Idaho National Lab site in Idaho, and there's a map there on the left to give a bit of a scale. It will be replacing actually the generation from the NuScale SMR. It will be replacing some portion of the existing and soon to be retired coal generation in the region. So although this is at an INL site, at a national lab site, and not directly at a coal-fired station, the ability to replace some coal generation in the region is what's driving this project, and will drive other projects. We've seen an increase interest in nuclear from those that have coal plants that are subject to retirement because of carbon legislation, and so increasingly the market is looking for alternatives, both from a carbon-free point of view and a reliability point of view. So from an international standpoint, we're also seeing a fair amount of interest. It was mentioned earlier that we're working with the CNSC, the Canadian Nuclear Safety Commission. We've actually made two submittals. The second submittal completed in December of 2020, and that we were also audited by the CNSC at that time. What was mentioned earlier, another word on the Memorandum of Cooperation between the CNSC and the US NRC, an example of where that cooperation can have merit. As I think was mentioned earlier, Canada is very familiar with CANDU technologies, and they have very little experience when it comes to light water technologies and the fuel that's used in a light water nuclear power plant and the coolant itself. So there's a tremendous amount of data at the disposal of the US NRC when it comes to light water, pressurized water reactor fuel, its characteristics, how it operates, and all the things that a safety regulator would be interested in. As a result of the Memorandum of Cooperation, and NuScale has been identified, and the NuScale technology has been identified as an opportunity where an exchange of information can occur. The US NRC is supporting the CNSC in the evaluation and providing the data to the CNSC to evaluate the fuel. And again, to the point that Anna made, CNSC very much feels the responsibility of their sovereign responsibility to protect the safety of the Canadians, and they want to review it, but they don't need to necessarily start from square one, taking advantage of the data that's been created, and evaluating that data certainly helps the process from the standpoint of efficiency, if you will, and not trying to recreate something that may already exist. Additionally, we're working with in the UK. We have MOUs in Romania, Czech Republic, Jordan, and a number of other locations globally, many of which are under NDA protection at this point. So from our point of view, the future is here. What you see at the bottom is our simulator in Corvallis, replicating what you would essentially find in a control room. And again, this is something we've demonstrated to the US NRC. And at the top right is our test facility at Oregon State University, where we've demonstrated the technology and building upon that information to start the construction process in the US. So I think I'll stop there. Again, thank you for the opportunity to speak, and I'm happy to answer any questions.
Thank you very much, Tom. Super interesting, of course, and I have quite a few questions, and I also see quite a few questions in the Q&A there. Some of them quite technical, so I encourage you to perhaps take a look at them also afterwards. One, you mentioned this $2,850 per kilowatt. I think that's the number that many people look at, and some, like myself, might be more familiar with the levelized cost of electricity. I've seen you also made some forecasts on that number. can you give us at least a ballpark figure what you expect in terms of the cost of electricity in the nth of a kind reactor of this type?
Sure. From an nth of a kind point of view, what we're targeting is $65 per megawatt hour or less. In the UAMPS project, there's some risk sharing that because of the first of a kind nature that the DOE is supporting, and that's bringing that price down to roughly $55 per megawatt.